La 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 li la la la, la 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 li la la la, la 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 li la la la, la 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 la, la 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 li la la la, la 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 li la la la, la 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 li la la la, la 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 la.
Welcome to my classroom. In this lecture, we are going to discuss about one of the flow measuring device for open channels. Okay, when we say open channels, through which the atmospheric pressure is acting on it. That means there is a free surface of the fluid, and we can measure the flow rate of it when it is flowing through open channels. Okay, so when I say that, you can say examples for that are river. Okay, when you have river, what you have a open water is flowing in that one, so the atmospheric pressure is acting on it. Okay, so that way for now we are going to discuss about one of the flow measuring device, which is weirs and notches. So what is a notch? So actually, one is for a small scale applications and another one is for large scale applications. A notch is a small scale application one. So where we will have, for example, you have a metallic, you have a tank is there. Okay, you have a tank. Okay, so there is some input of fluid into it. Okay, so we have a level of the fluid in it up to certain height. Okay. So what we can do is how to measure the volumetric flow rate. We can have an opening in it. Okay, we can have an opening in it, and the fluid may be flowing across it. Okay, so that opening may be of any shape. It can be V shape, it can be rectangular shape, or it can be a trapezoidal shape or any other shapes. Okay, so it can be V shaped, rectangular shaped, or thing. So it is actually a metallic plate with a V-shaped opening. Okay, a rectangular plate with a metallic plate with a rectangular shaped opening, or a metallic plate with a trapezoidal opening. Okay, so that opening is a with a particular V notch means there will be a theta. Okay, so the theta to which the opening is made. Rectangular means you are going to have a length into breadth opening. So trapezoidal means a combination of these two. Okay, so essentially it is used in small scale, particularly in the laboratories. Okay, so when you want to measure the volumetric flow rate in your open channel, like this tank, let me say it's a tank in which a particular level of fluid is maintained. Okay, so the liquid is allowed to flow through this edge. Okay, so what we have is a metallic plate which is connected to one end of the tank, open tank, and the fluid is allowed to flow through the opening in the particular metallic plate. So the opening can be a V-shaped opening, a rectangular shaped opening, trapezoidal shaped opening, or others. Okay, so notch is a metallic plate with openings. Okay, so the opening can be V-shaped, rectangular shaped, or trapezoidal shaped, or other shapes. So essentially it is a flow measuring device for open channels, particularly of a rectangular tank type or open flow. So we connect it to one end of the tank. So that once this is fixed to the tank, so the liquid level should be below this H. Okay, let me say capital H is the total height of the notch. Okay, so the metallic plate height is there. No? The liquid is allowed to flow below this one. So that is the way we want to measure the volumetric flow rate of fluids through these metallic plates. Okay, so this has application in lab scales. And this metallic, what metals can be used? Corrosion resistant material can be used. So it can be simply made up of mild steel, bronze, stainless steel kind of thing. So any metallic plate can be used. But if you want to be corrosion resistant, you have to ensure that fluid doesn't react with one. So we have to choose the material of construction of these notches such that it is chemically inert or it doesn't react or corrode easily. Okay, so we want to make these notches made up of corrosion resistant material. Okay, and these notches, so essentially we are having a opening here, so that when we call that opening, okay, the liquid is flowing across it. Let me say up to here is the liquid level. The liquid is flowing through this opening. Okay, so this zone in which in this V shape, the zone in which the fluid is flowing is called as sill or crest. So crest or sill is the portion through which the fluid is flowing in the notch itself. Notch is having this much height. Okay, as I said, the notch height is this much, capital H. Okay, and the liquid level is H, small h, from the free surface. Okay, so you have up to certain height, we are having the liquid fluid flow. From a depth of H, we are having the fluid flow across the metallic plate. Okay, so this is a notch. So notch is a volumetric flow rate measuring device for open channels, particularly of small scale, like a rectangular tank in a laboratory. Okay, and this notch can be of different shapes. It can have a V-shaped opening or triangular shaped opening. It can have a rectangular shaped opening, or it can have trapezoidal openings. Okay, so how we can, this is about the notches. And what is a weir? A weir is similar to notch, but it is used for large scale application like rivers. Okay, so if we coming back to weirs is like, you say we have a reservoir tank. What we make is, we make a cement concrete structure. It's a side view. Okay, so again it is similar to this notch. Only thing is we have a complete structure like this opening. Okay, a weir is made up of usually concretes, mason structures. Different concretes it can be. Okay, so again in side view it is like you make a wall and you are storing water in this one. Okay, and let me call it, it is the reservoir. Okay, so water is there. So water level is such that above this concrete structure we allow the fluid to flow past. Okay, so this is the, again, so you have fluid up to here. Okay, so this is actually upstream side. We have upstream side, we have downstream side. Same, here also it is upstream side. So this is downstream side. So the fluid is flowing out. Okay, so in the downstream side. So here the portion above, the portion of the concrete wall or the structure above which the fluid is flowing up to certain height, this is called as crest. Okay. Here also it is the portion in this opening above which the fluid is flowing is sill or crest. Here also the portion at the top over which the liquid is flowing is called as crest, and this is maybe a reservoir of height capital H. Okay, so we will not concerned about that. So it is a reservoir, let me say. Okay, so in the downstream side the liquid level is there, small h. In the upstream side there is a height capital H. Okay, so the fluid is passing through this structure. Okay, actually the application of weir is that it is similar to a dam. You store water here and whatever is the excess water is allowed to pass over this one. Okay, so that way it is also facilitating the water flow. and this acts as a dam also. So in earlier days, weirs means a small dam. Okay, so there are some advantages of these weirs which helps us to measure the volumetric flow rate of the fluid. Also, it helps us to maintain or control the flow in different directions like dams. Okay, and there is a flip side of it. Whenever there is a low head thing, suddenly there is changing. So somebody is traveling or boating or swimming, people are doing. Suddenly there is a small reservoir and it means that there will be a small change in height head of the liquid. So suddenly they feel discomfort when they are passing through it, and aquatic life also getting affected when there is a change in height. The head is suddenly getting reduced, right? So that way there is a flip side of using weirs. That is, one is the swimmers find it difficult, aquatic life gets affected. Okay, that's about weirs. So how we will determine the discharge through weirs or notches? Fundamentally they have same principle. Okay, so that we will derive. So for that we will consider a fluid element in a particular thickness. Okay, so what we will do for a general geometry, later we will move on to a specific geometry. Okay. Okay, what we will consider is, let me say, we have a opening like this. Okay. So in that, liquid is flowing like this. Okay, so water is flowing out of this metallic plate. We are considering a notch metallic plate with a dissimilar opening. Okay, we are not fixed the opening whether it is V-shaped, rectangular shaped, or trapezoidal shaped. So we consider a dissimilar shape. Okay, so let the total height of the fluid. So here it is the bottom, right? So let the fluid height is, total height is capital H. Okay. So let capital H be the height of this notch, and let it be, okay, yes, let capital H is the height of the fluid. What we will consider is, we will consider a small element. We will consider a small element we will consider a small element of thickness dH, and let it be at a height of small h from the topmost layer of the water. Okay, so you have water, and that from the free surface, we call it as free surface. From the free surface, you consider a small element of fluid, okay, of thickness dH, and at a depth of h. Okay, at a depth of h meters from the free surface, we consider a small element of fluid of thickness dH, and let the breadth at this point, be B. Let the breadth at this point be the meters, be the width. Okay, what is the thickness of the plate? That is dH meters. And where this element is there, the element is situated h meters from the free surface. Okay, let capital H be the total height of the fluid flowing across this notch. Let capital H be the total height of the fluid flowing through this notch. Okay, now what is the area? What is the area of the flow? Area of the flow? Area of the cross section of flow. Area of the flow is area of fluid flow. Area through which the fluid is flowing is B into dH. Area through which the fluid is flowing is B into dH. Okay. Now, B into dH is the volumetric flow rate. That is the flow rate in this small thickness, right? Now, from Torricelli's equation, we know that what is the volume velocity through this height dh. What is the velocity? Velocity is given by square root of 2gh. Right? From Torricelli equation, we have v equal to square root of 2gh. Okay. Now, what is the volumetric flow rate? What is the discharge? What is the discharge dq in this stream? Discharge dq through this stream is given by area into velocity. Okay. So, what is the area? It is b into dh into square root of 2gh. Okay. So, the velocity is square root of 2gh from Torricelli equation. For any flow measuring devices, we could able to establish that at any point velocity is square root of 2gh. So, the velocity of the stream is given by square root of 2gh. And we have b into dh square root of 2h as the dq. Okay, so we have an expression for dq through this strip. So this is at particular height dh, but the height varies from 0 to capital H. The volumetric flow rate varies from 0 to capital Q, right? So we can integrate it within the limits, integrating between the limits 0 to Q and 0 to H, we will able to get what is the discharge through the notch. So discharge through the notch can be given by integrating from 0 to Q dq is equal to b into, okay, square root of 2g is constant and b is a function of height, because this length will vary depending upon whether the stream we are considering is here or here or anywhere, right? So b is a function of h when it is dissimilar in nature. So we have b into square root of h dh. Okay, so that is, it varies from 0 to capital H. So this is the, before integration we have an expression for discharge through a notch of any dissimilar shape with the width. What we consider is, we consider a small strip of width b which is at a depth of h from the free surface and which has a thickness of dh. So the area of the fluid flow is through the strip is b into dh. Okay, and from Torricelli equation we have what is velocity is related to height hs, v equal to square root of 2gh. Okay, so the discharge through the element, discharge through fluid element, discharge through the element considered element of the thickness dh is given by dq equal to area into velocity, and area we have written b into dh. Torricelli equation velocity is given by square root of 2gh, and integrating from the limit 0 to q, 0 to h. As we change from 0 to h, the volumetric flow rate will vary from 0 to q. Okay, so that way what we get is q theoretical. Okay, q minus 0, it is q, and that is theoretical discharge, which is equal to square root of 2g and integral b into square root of h dh varying from 0 to capital H. Okay, so this expression is what we have for theoretical discharge for any dissimilar shape, and if we include the actual discharge is always less than the theoretical discharge, right? And we define it with the coefficient of discharge, and what we get as q actual is equal to cd into q theoretical. So this q theoretical is what we have. Okay, so that we are going to get. Okay, so q actual by q theoretical is coefficient of discharge. So q actual is equal to q theoretical into coefficient of discharge. So we have qa equal to cd into square root of 2g integral 0 to h b into square root of h dh. Okay, now we can derive the expression for a specific shape. For general shape, this is the actual discharge. So what do you have? Actual discharge is equal to cd into q theoretical, which is square root of 2g, into integral 0 to h b into square root of h dh. Okay, so this is a general expression for any shaped notch. For any shape of the notch, we have a general equation, and if we are able to define the shape, we will able to get actual discharge through different notches. Okay. So what we can do, first we will consider a rectangular notch. So if you consider a rectangular notch, what is that? B is constant. If it is a rectangular notch, your B will not vary with as a function of h, right? B will not vary as a function of h. Okay, so only as the h varies, your Q will vary. Okay, so depending upon the height of the fluid, you are going to have different discharge. Okay, so when the width is constant, what is the rectangular notch coming into picture? What the actual discharge you will get? QA is equal to CD into square root of 2G. B also comes out, which is the width. Okay, so then you have 0 to h square root of h. Square root of h I can write h power of, okay, dh. So this is the expression for a rectangular notch. So Q actual for a rectangular shaped notch. Q actual for a rectangular shaped notch is given by CD into square root of 2G. B is constant for a rectangular notch because it won't vary as a function of height. Okay, so in that case what happens, B will come out of the integral. So then we have simply 0 to h power of dh. So after integration, what you get is CD into square root of 2GB into B, h power 3 by 2 by 3 by 2. So which we can write here 3 by 2 as 2/3. So Q actual of a rectangular notch is given by CD was there, to square root of 2G was there, B was there, B is the width in meters. Okay. For a rectangular notch, B is constant, so it came out of integral. So h power of became h power 3 by 2 by 3 by 2. So we get Q actual of a rectangular notch is 2 by 3 CD square root of 2G B into h power 3 by 2. Okay. And this is about rectangular notch. So we can say Q actual is proportional to h power 3 by 2 for rectangular notch. For a rectangular notch, QA is proportional to h power 3 by 2. Okay. Can you derive for triangular notch now? Try for triangular notch. You can say triangular notch or V notch. Okay. We can do it for do the derivation for triangular notch. So for that we have to consider a triangular notch, right? So in that we will consider a fluid element of thickness at particular height. Okay, we have a particular width B, and which is from the free surface, it is at a depth of, let me say, small h meters, and let capital H be the total height of this one. Okay, so we are having fluid. Okay, what is this? Sill or crest. So the fluid is flowing over this metallic opening. It's a metallic plate. Okay, so we are having fluid up to this level, let me say. So we consider a small fluid element with width B, which is at a distance of, let me say, h meters from the free surface. Again we have a free surface. Okay, from a height of h meters from the free surface, let a capital H be the total height, that is from the edge to free water surface. The height is h meters. This is small h meters. Width at any point, let we are considering a small fluid. Again, we are considering a small fluid element of thickness dh. Okay, so we consider a fluid of element small h as dh, and which is having a thickness of b. So we have expression for QA like this. Okay, so now for a triangular notch, b can be like in rectangular notch we have taken out this b because b is fixed. Okay, whereas for a triangular notch, what we have to do with b? B is a function of h. Okay, so b is a function of h. How it is related at any point? How we will get that one? Let the triangular notch have a angle of theta. Okay, so then if you consider if a triangular notch, we have an angle theta. So if you consider only half of it, what do you have? This theta is, this angle is theta by 2, right? We have theta by 2 if you consider only half of the triangle. Okay, so we have theta by 2, and this opposite side is, this total width is b, so this will become half b by 2, right? So this total width is b, the fluid level is b, and this is going to be b by 2. Okay, now what is this height? This is, what is this height? This height is h, this height is capital H. Then what is this height? This is h minus small h. Okay, so this theta by 2 we have seen, and this is a right angle triangle. Okay, so you have theta by 2 here, this side is b by 2, this is h minus h. Then what is tan theta by 2? Tan theta by 2 is opposite side by adjacent side, which is b by 2 divided by h minus h. So we can rewrite to get what is b. B as a function of height. B as a function of height. B is equal to 2 into, this 2 goes to the right hand side, h minus h tan theta by 2. Okay, so we have width b at a particular height small h from the free surface as b equal to 2h minus h tan theta by 2. Okay, so can we substitute this into this equation now? We are going to get an expression for triangular notch. Okay, so we have QA equal to CD into square root of 2g, 0 to h, b into square root of h dh. So you have QA equal to CD into square root of 2g into 0 to h, b, now we are having b as a 2 into, let me write it fully once, 2 into h minus h tan theta by 2 into square root of h dh. Okay, now 2 tan theta by 2 can be taken out, so we can write q actual is equal to cd into square root of 2g into, so you can write 2 times cd. Okay, so q actual is equal to 2 cd into square root of 2g, okay, tan theta by 2 into integral is h into h power of minus h power 3 by 2 into dh. Two tan theta by 2 has taken out of the integral, h minus h into square root of h. Okay, so therefore when you write it as 2 terms, you have h into square root of h minus h power 3 by 2. Okay, now this integration limit is between 0 to capital H. So integrating between same way. Okay, so here also we, what we did, when you are integrating between 0 to h, volumetric flow rate varies from 0 to q theoretical. Okay, introducing CD only, we wrote QA. Okay, so now 0 to h into h power of h power 3 by 2 dh, it's simple integration what we are going to get. Okay, so you have 2 CD square root of 2g tan theta by 2. Don't cancel this to theta by 2. It is actually tan theta by 2. Okay, some people make the mistake. Okay, now, so what is the integration here now? H into, after integration what you get is h into small h power 3 by 2. Okay, so 3 by 2 is here, minus h power 5 by 2 divided by 5 by 2. Between the limit, integration limit is 0 to h, we have to substitute. Okay, now 3 by 2 is here, we have 2 by 5 here, 2 is here. Okay, so that can be going out. So now we will see what we can do now. Okay, substituting the upper limit and lower limit, we substitute h here, small h here, we are going to get h power 5 by 2, small h power 5 by 2. But these two terms are different. What is that different term? We will see. Let me write it this way, just for convenience. I am writing two steps. But if you understood, you can write directly. What we have is 2 by 3 h power 5 by 2 minus 2 by 5 h power 5 by 2. After substituting upper limit and lower limit. Okay. You have all these terms. 2 CD square root of 2G tan theta by 2. Okay. Now what is this one you will get? You are going to get, you have to make a denominator of 15. So 3 is there, 5 2s are 10, h power 5 by 2 minus 5 is there, 3 times 6. So 3 2s are 6 power 6 into h power 5 by 2. So 10 minus 6 is 4 h power 5 by 2 by 15. And 4 is what you are getting. Here 2 is there. So finally what we get is, so what we get is 10 minus 6, 4. So we have 4 into 2, 8. So we are going to get 8 into CD into square root of 2G into tan theta by 2 into h power 5 by 2, denominator 15. So that is our Q actual for a triangular notch or V notch. Okay, I repeat fully because you should not get confused. Actually, we will be writing Q theoretical first, then we will write Q actual CD, but I derived this general case, so that's why I am proceeding from general case to specific case of a triangular notch. We are considering a triangular we are considering a triangular notch with an opening angle. That opening angle is 2 theta. Okay, so we consider a triangular notch with an angle theta, and the total height is h, and we consider a small fluid element of thickness dh at a distance of h meters from the free surface. Total height is h meters. So now here we get the same expression, 0 to h, b into root of h into dh. Now we have to express b as a function of h. For that we use the definition of tan theta by 2. So we consider only half of this element. So tan theta by 2 is equal to opposite side by adjacent side. Opposite side is b by 2. Adjacent side is h minus h. So taking h minus h to the right hand side, denominator 2 to the right hand side, what we have is 2 into tan theta by 2 into h minus h. So that's what we substitute here. 2 into h minus h tan theta by 2. Then we have square root of h into dh. So this 2 into tan theta by 2 can be taken outside the integral, and then we integrating between 0 to h. We get h into h power 2, h power of into h power 3 by 2. After integration we get h into h power 3 by 2, h power 5 by 2, with these values coming, power values coming as the denominator, and simplifying, what we get is Q actual equal to 8 by 15 CD into square root of 2G into tan theta by 2 h power 5 by 2, where theta is the angle of the V blade. So if the angle is going, what is, we can see the effect of angle also from this one. So in comparison between in comparison between rectangular notch and horizontal notch, triangular notch, we can say that Q actual for a triangular notch, Q actual for a V notch is proportional to h power 5 by 2. Whereas we have already seen Q actual for a rectangular notch is proportional to h power 3 by 2. Here it is proportional to h power 5 by 2. So when the opening is triangular notch, the volumetric flow rate is proportional to h power 3 by 2. For triangular notch, it is h power 5 by 2. When the opening is a rectangular notch, the volumetric flow rate is proportional to h power 3 by 2. Now comes to the third derivation. What is the derivation for a trapezoidal notch? Okay, for a trapezoidal notch, what will be the derivation? So what is a trapezoidal notch? Actually, trapezoidal notch is, you have a V notch and a rectangular notch. What we get is, you divide it into two, attach this to left hand side, attach to the right hand side. What we have is, so it is a trapezoidal notch. Okay, so a trapezoidal notch is actually effectively a summation of a triangular notch, okay, plus a rectangular notch is the trapezoidal notch, right? So whatever is the discharge through this rectangular shaped opening, and you remove that rectangular shape, you have a V notch, triangular shaped opening. So the discharge through this triangle plus this rectangle gives me what is the discharge through this trapezoidal notch. So once we understood that, writing the discharge equation for a trapezoidal notch is simple, because already we have derived the expression for discharge through a triangular opening plus discharge through a rectangular opening will give me the discharge through this trapezoidal opening. So the discharge through a trapezoidal opening is equal to discharge through a triangular notch plus discharge through a rectangular notch. So we have equation for triangular notch, which is 8 by 15 CD into square root of 2g tan theta by 2 h power 5 by 2 plus, okay, for rectangular notch, what is the equation we have derived? We have derived 2 by 3 CD into B square root of 2g h power 3 by 2. So simple equation we derived for rectangular notch, discharge through rectangular notch, and discharge to triangular notch, we just derived 8 by 15 CD square root of 2g tan theta by 2 h power 5 by 2, and summation of these two gives us the discharge through a trapezoidal notch. Okay.
Well, we have derived the expression to determine the discharge for a triangular notch, for a rectangular notch, and for a trapezoidal notch also. Now, in that we have defined what is CD, right? CD is coefficient of discharge. And to determine the CD, we have an equation called, there are several empirical equations available. One of them is Raybock equation. So Raybock equation is to find the CD of a rectangular notch. Okay, so to find the CD of a rectangular notch, we have an expression CD equal to 0.605 plus 1 by 1000 H plus 0.08 H divided by P, where actually if you have a weir rectangular notch, the flow will be flowing like this. So this height is called P, okay, and this height is called H. So we have H and P as the parameter. Parameter is in the upstream side, what is the level of the liquid, and P is the height of the crest from the bottom. So actually it is the downstream side, what is the fluid it is flowing, that is the total height H. Okay, so this is the only empirical equation to determine the CD, and apart from that we have a Francis equation. Francis equation is an empirical equation to determine the actual discharge. Okay, to find the discharge over a rectangular notch, we have Francis equation, which was based on the experiments. He established the number of contractions. For example, if it is a submerged flow, there are no contractions in the fluid. So this is the cross-section area of the fluid flow. Okay, so now when you introduce the opening, let me say we are introducing an opening of like this, that is one way. Other type is one side is now contraction, other side is there is contraction. Okay, so we have contraction here. Here it is submerged. So when we have n equal to 0, we have n equal to 2, and we have n equal to 1. N is the number of contractions. Number of contractions. So based on which we have an expression called L equal to we have L is equal to we have Q equal to 2 by 3 CD into B minus 0.1 N into H into H power 3 by 2 into that square root of 2g will be there. So square root of 2g. Okay, so where n is the number of contractions. So number of contractions means if in the cross section area of the flow, how many contractions are there. For example, if a rectangular notch is at the center, there are contraction in this side and contraction in this side. So number of contraction equal to 2. Okay, when the notch is connected at one end, so there is a flow of fluid across from the one end. So contraction is from one end. So we have n equal to 1. When over this when this notch is there, okay, so the fluid is flowing all over the notch. That means the contraction is 0. So that is called submerged notch. So in that case n equal to 0. So we will be substituting n equal to 0, n equal to 1 and n equal to 2 when the number of contraction equal to 0, 1 and 2 respectively, and B and H are standard. So B is the width of the fluid or length of the weir, okay, and H is the height of the liquid flowing over it. Okay, so this equation will be used to determine the discharge using this empirical equation, which is called as Francis equation. Okay, and we have Rebock equation, which is used to determine the discharge, which is given by 0.605 plus 1 by 1000 H plus 0.08 H by P, where H is the, say for example, is the weir. So in the upstream side, what is the height of the fluid, and in downstream side, what is the height, that is called P. Okay. You can say even this is the crest. This point is called the crest. It is the height of the crest. Okay. Now we will solve some numericals. Okay, so we will solve some numericals under this topic. So for example, first we will solve a numerical rectangular notch. Okay, so a rectangular notch 2 meters wide has a constant head of 500 meters. Find the discharge over the notch if coefficient of discharge a rectangular notch 2 meters wide has a constant head of 500 mm. Find the discharge over the notch if coefficient of discharge for the notch is 0.62. Second part is there, instead of the 2 meters, if it is 8 centimeters wide, instead of 500 meters mm height, what is if is 15 mm. Okay, let me solve this B part first. Okay, so how we solve this problem? There are two parts. Let me say A part has width equal to 2 meters, h equal to 500 mm, and we have B part which has a width equal to 8 centimeters, that is equal to 0.08 meters, and h equal to 15 centimeters, that is equal to 0.15 meters. So for a rectangular notch, we know the discharge, actual discharge is equal to 2 by 3 CD into square root of 2G, right? B into H power 3 by 2. So we have CD value we have to take. It is asked to, we have given CD equal to 0.62. So what we have written here is a given data. We can even draw a diagram. Okay. So where B is the width and H is the liquid height. Okay. H is the liquid height. So substituting, we will get the answer. It's a straightforward application. You can try it. Okay. So what you will substitute? You substitute B equal to 8 centimeters, H equal to 15 centimeters. So what we get? Let me do it for B part. So what we get is 2 by 3 into 0.62 into square root of 2 into 9.81 into 0.08 into 0.15 power 3 by 2. Please use the calculator. What we get is meter cube per second. Okay, so that is 0.085 meter cube per second. Similarly, for this is for B part. So A part, we will get Q actual equal to 1.29 meter cube per second. Okay, it's a straightforward application. I hope you are getting the answer. Okay. So now we will move on to the next problem. So we have another problem where it is given that a rectangular notch has a discharge of 0.24 meter cube per second. When the head of the water is 800 mm, find the length of the notch. So how to find this problem? How to solve this problem? So find the length of the notch. Assume CD equal to 0.6. So it's easy to find that, right? B is asked. In reverse, we have to find. So in the formula, we know only unknown parameter is B. Okay. So again, so coming to that problem, it is given that Q is equal to 0.24 meter cube per second. When the head of the water is 800 mm, that is 0.8 meters. What is B? It's straightforward application, right? Q equal to 2 by 3 square root of 2G CD into, we have B into H power 3 by 2. That is for a rectangular notch actual. Q actual for a rectangular notch is given by this. B is the only unknown parameter. Rearranging, you will get B equal to this much meters. Substitute the values. G is 9.81. CD is given 0.6. Okay, H value is given 0.8 meters. Q is known 0.24 meter cube per second. Substitute and rearrange to get what is B value. So you will be getting around B value 189.189 meters, or you can write as 189 mm. Okay, so that is the other problem. So we have solved these problems 1, 2, and 3. So that is done. This is done. Now coming to this problem, a right angled V notch was used to measure the discharge of a centrifugal pump. If the depth of the water at the V notch is 200 mm, calculate the discharge over notch in liters per minute. So in LPM, what is Q? That is the question. Okay, find Q in LPM. Assume coefficient of discharge as 0.62. Okay, so now we can solve this problem. So we know all the given data. Okay, we should know what is the formula first. Q actual is given by 8 by 15 CD into square root of 2G tan theta by 2. Then what else you have? Tan theta by 2 H power 5 by 2, right? For a triangular notch, we have this formula. So CD value is given 0.6. Q is given so what is the Q value? a q value is given as, okay, question is find the q value. So it is given that v notch is a right angled v notch. That means theta is equal to 90 degree. Okay, so theta is 90 degree is given. So we will able to solve this easily now. Okay, cd value is 0.62, it is given. So I verified. H value is given. Q is we have to determine in meter cube per second. Then we have to convert to LPM. Okay, so then H value is given as 200 mm, so which is equal to 0.2 meters, and theta by 2 is, yes, it is given theta is 90 degree right angled, right, it is given right angled notch. Okay, so theta by 2 is 45 degree. So what is tan theta by 2? Tan theta by 2 is equal to tan 45. We all know that tan 45 is 1. Okay, so then what you have is g value we know to 9.81 meter per second square. So we have CD value 0.62, G value 9.81 meter per second square. Tan theta by 2 is, that is tan 45, and H is equal to 0.2. So we are going to get the straightforward answer in meter cube per second. So how much is this answer in meter cube per second? How much we get is 0.026 meter cube per second, but we have to convert it to LPM, right? So how to convert it into LPM? We know that 1000 liters is equal to 1 meter cube, and 60 minutes, 60 seconds is equal to 1 minute. Okay, so this meter cube will get cancelled, second will cancel. So what we get is LPM. Okay, please comment your answer. How much is your LPM? You should be getting around 1560 LPM. Okay, so 1560 LPM is what we get. Okay, so that is the answer. So next one is, we have another problem, a simple one. Well, this is the fourth problem. A rectangular channel 1.5 meters wide has a discharge of 0.2 meter cube per second, which is measured in the right angled V notch. Find position of the apex of the notch from the bed of the channel. Maximum depth of the water is not to exceed 1 meter. Assume CD equal to 0.62. Okay. Now, again we are going to make use of the same formula, that is Q actual equal to so this is for triangular knots. Q actual equal to 8 by 15 CD into square root of 2G tan theta by 2 H power 5 by 2. Okay. So in this numerical, what is given? So in this numerical, we have a given Q is given, Q equal to 0.2 meter cube per second. Okay, and it is given that the triangular notch, it is a triangular notch is a rectangular, what you call right angled notch. Okay, that means theta equal to 90 degree. So tan theta by 2 equal to tan 45 degree equal to 1. Okay, so we know the formula Q is equal to, Q actual is equal to, for a triangular notch it is 8 by 15 CD into square root of 2G tan theta by 2 into H power 5 by 2. So in this problem what is given is, it is not only asking what is H. Okay, not question is not just H. Yeah, obviously we will find H using this formula, but also it is asked what is the, because it is a V notch, right? Apex point means this. So what is this height is asked. So if you know it, and also it is mentioned that the total height of the water level. So the total height of the water level cannot cross 1 meter. So then what is this small h? Let me say if it is P. Now what is this P? P equal to total height minus h. Okay, total height is 1 meters minus this much meters. We get P meters. So what is the apex height can be determined once we know the h value. How we get h value for a right angle triangular notch? So we have this formula. So substitute the given data. We have 0.2, okay, equal to 8 by 15 into CD value is given as 0.62 into square root of 2 into 9.81 into tan 45 is 1 into h power 5 by 2. So simplifying, we will get h equal to this much meters. So what is the answer? Please do the calculation. So we get h equal to 0.45 meters. So then what is the height of the apex? The height of the apex is given by 1 minus 0.45, which is 0.55 meters. So that is the height of the apex. Okay. Now we have one more numerical. So what we have seen so far is a single weir, okay, single notch. Okay, let me say it is a single rectangular notch. Okay, so what if we have a notch which varies in length like this? So that means that we have fluid is flowing across this. Okay, so this height is h1 and we have a breadth of this rectangular notch b1. Okay, so we have this b2 and we have h2, this is h1, and we have b3 and h3. Okay, so we have h3 b3. So this type of weirs are called as stepped weirs. Okay, so this step can be even also like this. First we have a v-shaped opening, above which we will have a rectangular shaped opening, right? So there is a possibility the water is flowing across it. So here the water is flowing across this, right? So what we have, so this q of the triangular notch plus q of this rectangular notch will give us the q total here, right? So that way we can determine the overall notch, because if we know the h1 and b1, and if we know h2 and theta, from h2 comma theta we will get q of the triangular notch. From b1 comma h1 we will get q across this rectangular section. So summation of these two will give us the overall notch, overall discharge over the notch. Okay, now what about this type of notch? What will be the q total? So we are going to have q1 across this section of a, so q1 is a function of h1 comma b1, q2 is a function of h2 comma b2, q3 is a function of h3 comma b3, right? Now what is q total? So, because this is the total area through which the water is flowing, okay, the fluid is flowing. So q total is equal to q1 plus q2 plus q3. Okay, so that way if it is a stepped weir, stepped weirs or stepped notches, we will get the overall discharge equal to summation of discharge through the opening 1, 2 and 3. Okay, so that summation will give us the q total. Okay, so we can even solve a numerical in that fashion. There are several gate questions which are asked with this type of stepped weirs kind of problem, because it takes care of how it is proportional. Q is proportional to the parameters, different parameters. Okay, so that way if you look at this numerical, So we have find the discharge in meter cube per second over a stepped notch shown in this figure, and it is given that h1 equal to, so we have h1 equal to 400, all dimensions are in mm, so it is 400 mm equal to 0.4 meters, and b1 equal to 1200 mm, which is equal to 1.2 meters. Okay, similarly here h2 is given, h2 is equal to 0.2 meters, and b2 is equal to 0.6 meters, and here h3 is very small, h3 equal to 50 mm, which is equal to into 10 power minus 3, so 0.05 meters, and b3 equal to, it's given 150 mm, so which is 0.15 meters. So as I said, q is equal to, q total is given by q across 1, let me say this is 1, 2 and 3, q1 plus q2 plus q3. For a rectangular notch we know the formula, right? So we know the formula. So what is for rectangular notch? It is q equal to 2 by 3 square root of 2g, okay, cd into b into h power 3 by 2, right? So if these are common, right? So this is for any q actual. So if there are three sections are there, so how we can write q total? Q total equal to 2 by 3 square root of 2g into cd into b1 h1 power 3 by 2 plus b2 h2 power 3 by 2 plus b3 h3 power 3 by 2. Okay, so substituting the values of h1 b1 h2 b2 h3 b3, we will get the final answers in meter cube per second. Okay, so please solve this problem and report the answer, because they asked you to find what is the discharge in meter cube per second. Even sometimes if they ask you to report in LPM, you can convert and report. Okay, so this problem it is enough if you stop at meter cube per second. Okay, all of you please comment the answer. If you are watching this video, you have to comment the answer of Q total of this problem. Okay.
So these weirs and notches are important flow measuring devices which have been used for a long time. Even before the civil engineering, chemical engineering came into picture, people have been using this type of thing to control the fluid flow and control the volumetric flow rate also. Okay, so that's about the weirs and notches. Well, in this lecture, we have discussed about the construction of weirs and notches, what is the difference between them, and how to derive the working equation for a rectangular notch, a triangular notch, and a trapezoidal notch. Thank you so much for joining my classroom. Meet you in next video. Bye-bye.
Tak nu verás, im cirto are la sahimae linche linchane, siru dhamare le la